Welcome to all the speakers for this session on power system flexibility and DERMS in collaboration with AspenTech as part of India Smart Utility Week 2025. Thank you AspenTech joining us as a session partner for this session. It is my great honor to invite chair for this session, Mr. Ravinder Singh Dillion. He is a member at CERC. Welcome, sir. May I invite moderator for this session, Mr. Abhishek Ranjan, CEO at BRPL. Welcome, sir. I would like to invite theme presenters for this session, Mr. Anand S., Principal Solution Consultant at AspenTech India Private Limited. Welcome, sir. May I invite Mr. Terry Mohan, Chairperson, Microgrids, Australia. Welcome, sir. I would like to invite speakers for this session, starting with Mr. S.C. Saxena. He is a Director, Market Operations at Grid India. Welcome, sir. May I invite Mr. Rahul Chakrabarti, Director from AspenTech India Limited. Welcome, sir. May I invite Mr. Om Dubey, Director CCR Australia. He will be joining virtually with us. Welcome, sir. May I invite Mr. Akilur Rahman, CTO, Hitachi India. Welcome, sir. I would like to invite Mr. Suraj Basin, Digital Solution Architect at Grid OS. Welcome, sir. I would like to invite Mr. Devanand, Chief at Tata Power Company. Welcome, sir. May I invite Mr. Mohak Mangal, CEO and Founder, Prahak. Welcome, sir. Now I am handing over the session to moderator to take forward the session for further discussion.
Thank you, ISUW, for organizing and hosting this wonderful session on power system flexibility and DERMS, basically. And I'm very glad and honored to be a part of this very illustrative panel. My name is Abhishek, working with a utility called BSES in Delhi. And I am very proudly welcoming my co-panelists, starting with our chair, Sri Ravinder Singh Dillion, member CERC, and under whose guidance we will have this session ongoing. And may I please invite Sri Ravinder to give his opening remarks, and followed by which we will go through the discussions and and then followed by question and answer. Mr. Dillion, please.
Good afternoon, everyone. Thank you for this opportunity to chair this very important session and quite relevant in today's context. Power system flexibility and distribution, energy resource management system. So we have seen that renewable energies is coming in a big way in India, and because of the intermittency, we have to have other forms of supports with respect to storage and the variability which wind and solar brings in. It is very important that we have some sort of balancing power also. So flexibility becomes very important. Then we have seen in India the demand is increasing, and we have a target of 500 gigawatt by 2030, out of which 100 megawatt of solar we have already installed. And going forward also the load is going to increase. We have seen that 7 to 8% growth is there every year, and we have universal access. We have provided certain light points, fan points to our the rural households. And slowly they will need some sort of refrigeration and other forms of energy consumptions. So the power consumption is going to increase. And we have seen with this renewable coming in, the grid stability has become very important. In the month of August itself, we have seen that the frequency during the daytime has gone up till 50.4. So that is very a concerning thing for the grid, where we have a band of 50.05 to 49.9. So this concern is there, and during daytime, we do not have that flexibility of thermal coming down below the minimum of 55%. So they keep on injecting, and the renewables also are in full force during the daytime. So flexibility becomes very important. And we have seen that a technical minimum of 55%, the regulator is also saying that bring down to 40% in a phased manner. So that will support the system in a way. And obviously we have to support hydro projects, and Government of India is also pushing for that. And energy storage has become very important. The costs of energy storage are coming down. Pump storage scheme, where we can give support through hydro, that is also becoming very important. And we have seen that in India there is a potential of 120 gigawatt of this sort of energy demand response. We have to encourage that industrial and commercial consumers, if they can shift their demand, so that will also help the grid. And obviously the grid has to be monetized, and better forecasting and balancing has to be there. So with these, and the role of distributed energy resource management becomes therefore very important. And we have distributed forms of generation. We have solar rooftop, battery storage, and on the consumption side we have electric vehicles. So the grid has to be very resilient to take up this. And consumer participation is also going to increase. We have prosumers who can generate also electricity, and in some sort we can have some trading of that power. So I think I will pause at this and let the other panelists also give their views. Thank you very much.
Thank you, sir, for the opening remarks. And now I see we have two theme presentations. And I'll start with Mr. Anand S. He's Principal Solution Consultant, AspenTech India, Mr. Anand. And then we'll move on to Mr. Terry.
change it from here? This key?
Yes, you can.
Okay. It is not working. Yeah. Good afternoon, everyone. Myself, Anand. I am a principal solution consultant with AspenTech India. So today's session will be on power system flexibility and DERMS. I'm not able to change. I'm not able to shift to the next slide. Yeah. So just an outline of today's presentation. Just an outline of today's presentation. In this 20-minute presentation, we'll be talking about the transformation of power grids and the dual challenge, the power system flexibility and DERMS. Here we'll be talking about our DERMS product, which is called as Integrated DERMS. Then we'll be talking about how the DR registrations happen very briefly. For this, we'll be talking about our AspenTech Symphony and Grid Apps product. And lastly, we'll be seeing two case studies of DERMS implementation. I'm not able to shift the... Yeah. Regarding the first point, transformation of power grid and the dual challenge. So for this, I'll just take you back a bit back in time when the grid was a simple unidirectional machine. So the generation was centralized. The generation was centralized. It had a good amount of inertia in the system, and even to take those rare power swings. And the life of the operator was very simple, simple increase and decrease in generation. And so this was how the generation was controlled. Okay, with respect to load, the load patterns were fairly stable, and it was predictable. Even though cybersecurity risk was there, it was minimal. So these were the good old days. Now, coming to the modern grid, which we are having in the present day grid. So what has happened is, it has got a lot bigger, and there is an introduction of variable energy resources like renewable generation. So what this has done is, it has introduced variability in the system. Again, the output of these generations is dependent on God's will. We never know how much it is going to produce at any given point of time. Then on the other side, like we have battery energy storage. For the first time in history, we are able to store power efficiently. So that is a good thing. And next, when coming to the distribution side, now we have energy prosumers who are keen to produce more than consuming more. So these are some of the changes that has happened to the grid. And the inertia of the grid has come down due to more and more renewables getting added. So in a way, the network size has increased. It has become a bidirectional machine. Due to the number of interconnections and digitalization, the cybersecurity risk is also increased. So I'll be taking you through some of the hard facts, some well-researched facts that we have. By 2050, the size of generation is going to increase by 2.6 times, largely due to the increase in renewable generation. The size of the electrical grid is going to increase by 2 times, and this is mainly due to the increasing population and the electrification of almost everything. While we talk about decarbonization, we predict that by 2050, there will be 91% of renewable generation. And extreme weathers will ask the grid to be more stable and resilient. Even though in terms of there is grid weather disturbances. Due to digitalization, the cybersecurity threats over past 2 years has doubled. And with respect to the skill gap in the utilities, now the utility employees, they have to be reskilled in a different skills. So that is also a challenge. So this brings us to the concept of dual challenge. On one side, the energy demand is going to increase by almost 50%. And on the other side, we need to do this in a sustainable way. So in AspenTech, we call this as the dual challenge. And if you see, this is our main, we see this as our main business purpose. And all our AspenTech products are aligned to meet this requirement. Just a glance about our company. We are a global leader in industrial software for asset-intensive industries. We have some 3,000 plus customers and 40 years of innovation. We are spread across 41 countries. So this is a glance about our company. So coming to the product suites that we have performance engineering, manufacturing supply chain, asset performance management, subsurface engineering, and digital grid management, and industrial data management. We have got 6 product suites. So today we'll be focusing on digital grid management. So this digital grid management was earlier called as OSI. So some of the examples where we have our installed base. So these are some of the examples across the world. Now coming specific to India region, here if you see, our software is managing NLDC, which is the transmission EMS system for the entire India. So it is the world's largest synchronous grid. It runs on AspenTech Monarch software. Apart from that, we have around 10 state utilities which are running our transmission product. Then a couple of the north and south region REMCs. With respect to distribution, some of the major cities in the world run on AspenTech Monarch software. So this is with respect to India. With respect to Asia Pacific, we have installations in Malaysia, some installations in Australia, and like this. Yeah, coming to the topic of power system flexibility and DERMS. So what is power system flexibility? Power system flexibility refers to the ability of the grid to dynamically manage supply and demand, right? So it should handle the variability. On one side, it should handle the variability from variable energy resources, and at the same time, it should deliver stable power to a dynamically varying load. So this ability that is what is defined as the flexibility of the power system. Okay. On the other side, DERMS, it is basically a software platform which is used to monitor, control, and optimize the DERs. Right. So in this topic, we are focusing on DERMS as an enabler for power system flexibility. So what does DERMS specifically do? It controls the DERs in real time. It has got automated control where we can schedule the DERs based on the requirement. We can peak shave. So these kind of operations can be done. Interoperability, again, with the existing DMS systems, some third-party systems, interoperability is very crucial. AI-driven optimization is required for forecasting and other applications. Again, since we have many interfaces and many digital devices, cybersecurity is key. So that is also taken care. So this is our broad product portfolio under AspenTech Digital Grid Management. Many of you know AspenTech Monarch, OSI Monarch. So this is the same platform. Here you can see it is a comprehensive platform which covers the entire electricity value chain, starting from generation, transmission, and distribution. We have specific products for generation and transmission. For ADMS, we have products, and the DERMS product can be used for transmission as well as distribution. So as I said, this is a comprehensive platform, highly modular platform, which is used in several load dispatch centers and city distribution networks. So some of the challenges that utilities have in DR management and how DERMS is able to solve them. So first thing is end-to-end visibility of the DR. Like when the operator gets entire visibility on the DR, how much DR, what is the capacity, how much it is generating, what is the forecasted generation. So all this kind of information we can get. We can do real-time dispatch and control. Real-time dispatch in the sense curtailment is possible. Then, as I said, we can forecast the generation as well as the load. Then it allows the operator for like the utilities for market participation also. So this is our DERMS product architecture. So here, if you see below where we have the SCADA platform Monarch, which will interface with all the real-world devices. So this is the base for all our systems. And on top of that, we have the DERMS model, where the physical DERs are modeled. We do have physical modeling, and we do have contractual modeling for market participation. And on top of that, we have the different functions which the utility can pick and choose. We have functions for visualization, we have functions for forecast, scheduling, economic optimization, we have a microgrid management system, VPP management, like this. So it is important that this system interfaces with enterprise systems like GIS, market, AMI, and weather services for forecasting. And we do have some third-party aggregation, we can interface with some third-party aggregators also. So some of the functions, main functions of the DERMS software. So first thing is visualization. As I told, the operator gets full visibility on the DERs. Again, as per the operator requirement, the visualizations can be changed. Here, the green circles that you see are the DERs spread across the network. Again, it can be visualized in different ways as per like in whichever way the operator wants, it can be visualized. Okay. Not only being visualized, it can be, we can also do a steady mode, and we can see what is the impact of this DER in future. So this kind of studies also can be done. Estimation and forecasting. So we can estimate the generation from the renewable sources. Okay. We use different methods to do this forecasting. Okay. We can do the forecasting without telemetry also, from the nameplate details of the solar panels or from bellwether forecasting. So these are some of the methods. We use AI and machine learning models to predict the solar generation. Scheduling and control. So here, what we do is based on the peak load, we can set how much generation is needed, okay, or we can set the peak shaving also. So based on that, the curtailment of the renewable generations takes place. We have virtual power plants where we can aggregate different DERs and dispatchable demand response loads spread across different areas, and same they can be controlled as a single VPP and different business models based on that aggregation can be achieved. So some of the differentiators of our DERMS product, I would just highlight few of them. We have a very good UI, okay, and it is the total cost of ownership is very less. It is very easy to maintain and update. Next, we'll talk briefly about DER registration. It is a big topic, but I'll just try to cover this in 2 slides. So recently, AspenTech AspenTech procured acquired a company called as Open Grid Systems. Okay. Open Grid Systems is basically a network model management company. It is based in UK. So here what happens is they are into network model management and DR registration. I'll just explain how it is done. So here if you see, we have an app through which the individual DR owners, they can self-register their DRs onto the network. And once it is done, all the data that the consumers enter will be directly loaded to the network model. So it is an easy way where the DRs can be registered to the network. We can show this product in detail in our stall. One more issue is whenever DRs comes up, there is the interconnection issue is there. We have a product which will automatically tell you which is the best route to choose for the interconnection. Again, this ability is given to the user, and based on this, they can quickly choose the best interconnection possible. Yeah, some of the DERMS case studies. I'll quickly go through the case studies where the system is already in use. So SMUD, it is a distribution utility in California. So here we have some 650,000 customers, and they have around 20,000 plus solar PV systems and 6,500 EVs and around 130 energy storage devices. So their requirement was for a DERMS system. So what we have offered is Spectra DMS, which is our ADMS product, along with the DERMS solution. So with which customers are able to manage the DRs, manage the distribution network, and also their DRs. The second example what I want to show you is SRP, Salt River project. So here, here we have around 1 million customers. And this is a full-fledged system, like it is a transmission, we have generation control, we have OMS and DERMS. So the highlight here is one system can cover all the parts from starting from generation till DERMS. So this is one more example where we have implemented. These two are like few examples, like out of many projects we have already implemented. Thank you.
Thank you, Anand. And this was a very good overview of what is happening and what you guys are doing in this space in the country, in India, and as well as globally also your footprints are there. And this is wonderful. I mean, talked about DERMS, ADMS, SCADA as a whole cohort, as a whole ecosystem. And then slowly we were talking also like when the DERs are getting more penetration levels, we need systems which is seamlessly integrated with our distribution SCADA, for example. ADMS and then hence DERMS, the grid edge technologies behind the meter, whatever resources that we have. And we're talking about like DER, real-time situational awareness, dispatch, control and forecasting as well. So that is wonderful. And we are also wondering that you talk about say millions of distributed energy resources given the size of a DSO, you would also need a very, very robust communication backbone. Okay, so those things will be very interesting to know. But then let me invite now Mr. Terry Mon, Chairperson of Microgrids Australia. Terry, we would very be interesting to look into what Australia is doing in this regard. Thank you.
Good afternoon, everybody. It's my pleasure to be here to speak with you today about some of the experiences that I've had deploying DERMS and beyond. My talk today is going to be a little bit more challenging, though. It's going to be the evolution of the grid where DERMS is the starting point. I hope you enjoy. So this is a quote that many people use over and over. Nothing is constant but change. And we're about to see and witness that in the utility sector in the next coming years. I actually forecast this presentation 10 years ago when I was working in the United States. I worked for a very large utility in North America, actually in California where SMUD is. I worked for a utility there. We deployed a DERMS back in 2007, 1.5 million endpoints. And after I finished that work, I realized that DERMS was a platform that could be used for multiple things. So as we watch the progression of change in the utility industry, it reminds me of the so-called evolutionary thought that people have about the evolution of the human race. I see something very similar occurring in the utility sector. My prior speaker did a really great job of talking about the architecture of the grid, particularly architecture of DERMS and how it sits in the utility operational stack. It's one that I've been involved in implementing myself, so it's actually a very good course study. So this is kind of the starting point of our evolutionary trip that we're going to be taking about the grid. Originally, we started looking at transition from analog to smart grid, which former speakers spoke really eloquently about. Then we started seeing the introduction of large-scale renewables in the utility, which caused variable energy resources coming into the grid that needed to be addressed. Then we saw the introduction of demand response and tools like power purchase agreements and this thing called non-wires alternative. We see this in other countries. I don't know that we've seen it here, but non-wire alternative is a concept that a utility is facing the cost of a substation upgrade that are very expensive. The example I want to give is in Santa Barbara, California, there are 2 transmission lines that hover over a very fire-intensive area. And so the local utility asked the industry how to upgrade the reliability of those substations if the transmission lines were to go out. And so the industry actually came up with suggestions of where they would make the investment in the software or in the system upgrade to the substation so that the reliability would be maintained and then also export any of their capacity back into the grid. It just so happens this was a very important city because that's where Oprah Winfrey lives. So it had to be reliable. We see also an increasing complexity in the IT-OT relationship. We need new skills for that. On the IT side, there is telemetry, metering, sensor technology, bidirectional power flow, which each have sensors. So all of that was explained earlier, but that also is one of the key things that's driving change into the industry. Then we see the rise in customer-owned assets, rooftop solar, EV batteries, EV charging. Some homes now are actually putting electric storage in their buildings. There's a whole industry around power walls and things of that nature. So the customers are actually taking responsibility of making investments on their own. They're not including the utility in their investment decision. They're actually looking at how do they provide their own energy reliability. But they could also be a resource, and that's where the DERMS comes in. Then we see areas where neighborhoods themselves are taking responsibility for providing the power. It's not only just a residence, but it could be a campus or a strip mall or something of that neighborhood, of that order. Sometimes what we've seen, though, is because of the export capacity coming from customers that the utilities have decided that they need to curtail it. And some of the measures have been draconian in that the utility will actually shut the inverter off, which causes the customer not to have any power from their energy resource at all. So we just needed to come up with a better solution for that. So what do we see happening in the industry because of these really critical issues that the utilities have to face? Number one, we talked about high concentration of distributed energy resources. Utilities start to implement DERMS. Then soon we start to look at the capability of transacting a monetary scheme between two users that are on the same circuit through using transactive energy. So there could be a marketplace for actually buying and selling your energy resource to others on that circuit. The utility can take a role in that by becoming a distribution system operator, which means that the utility creates a geographic region where all the transactions take place across hundreds, if not thousands, of individual users. That is very similar in nature to the transmission marketplace. So the tools in transmission can now be used as a tool in a distribution. Because we're able to now create these geographic areas that represent the whole of managing energy, it's starting to look a lot like a microgrid. So these are microgrids that are embedded in the network itself. A lot of times we talk about microgrids that are rural and remote, where there's no access to a utility, but I'm talking about microgrids that are starting to be formed now in many countries just because there's pockets of a geographic area where there's interest in managing their own power supply. As isolated microgrids become more prevalent, you'll find that there'll be microgrids adjacent to other microgrids. Once that happens, if you have an investor in one microgrid, you might have a second investor in a second microgrid. They may want to transact between each other, and that's where we call it a federated microgrid. So you have multiple microgrids that exist at the edge of the distribution circuit that are transacting on their own, but the utility is no longer a player. So what's happening when the utility starts to witness many of their large customers are creating microgrids? The utility itself, the holding company of the utility, needs to create a division that competes with the industry. And we've already seen that happen. So I come from North America originally, I'm now in Australia. I've seen this happen in both countries, where utilities now are creating microgrid divisions to compete with the investors that are pretty much eating their lunch. So why do we see the microgrids popping up? The first order of reasons why we see microgrids occurring is because that the infrastructure for the facility is critical in nature. So we see microgrids occurring, developing around airports, seaports, many first responders, police stations, and so forth. I personally have been involved in developing a microgrid for a military base and data centers. We know that data centers are becoming huge consumers of power. They need reliable power, and they also have to meet their emission goals for their corporation. So these are areas where we see the first instance of investments in microgrids. Hopefully, they become resources to the grid, but they can act independently. So if that's the first order of investments for microgrids, I think the secondary one would be coming in where neighborhoods decide that they want to be a microgrid, strip malls. We see many microgrids that are colleges and office campuses and hotels. I know of an example in the United States where there's a pharmacy store that has 2,200 pharmacy outlets. They've decided to create each one of their outlets into a microgrid. So we're seeing the evolution and growth of the microgrids quite pervasive. So we saw an architecture earlier from the prior speaker about the design of DER and DRM management. So this is the concept where you have many microgrids that exist within a neighborhood that now become transactive. And this is where the utility actually has a role. They can actually orchestrate the transaction between multiple systems, multiple microgrids, in the form of a DSO, a distribution system operator. I'm amazed that my slides look so similar to your slides in the former presentation. This is kind of the idea that we have where the utility now has a vital role to play, where microgrids start popping up at the edge of their system, but they want to have a very healthy relationship with those microgrid designs. And so we see them being the system controller for everything at the edge of the grid. And this is basically the primary role of the DERMS system, is to orchestrate across all of these different competing interests for the good of the whole. I mentioned the idea of federated microgrid, so this is where you have multiple areas within a city or within a region where they each have a kind of self-contained management of their energy portfolio. I actually have seen these being built. Many of you who are road warriors and travelers have been through the JFK Airport. JFK Airport 4 years ago began transforming their energy infrastructure into a federated microgrid. There's 5 microgrids now that sit on the campus, and it's a third party that actually is making all the energy investments in this, a company called Alpha Structure. They have a 99-year lease to sell energy to the airport. So we're talking about bankrolling huge investments in microgrids where the core feature of it is be able to transact energy. So I'm going to give you an example of a microgrid, an example of DER that was being installed in a microgrid in my state, Western Australia. This is an implementation that I did about 6 years ago. And I'm going to show you what happens before and after the implementation of DERMS. So this is a day where, like any other day, many solar rooftops are generating power back into the grid or into their home. But then the clouds start to come over. So those little bar graphs that you see are the output generated from individual homes going into the grid. The top graph is the aggregate of all the compiled system units. Now, once the clouds start coming over, you'll see the effect. So this is very destabilizing to the utility, and this is exactly why the DERMS system is needed, is to help mitigate against this crazy energy footprint. I've seen swings in a 12,000 volt distribution line as much as 1,000 volts up and down in any 1 second. So this is now the same area, same location, same units after the DERMS system has been deployed. I might point out that neighborhood energy storage was put in place on some of the circuits to help stabilize the grid, but the effect of managing all the individual units was quite dramatic to the safety of the circuit that was feeding all of these. You can see that at a certain point, the DERMS system kicked in and started either energizing the electric storage or curtailing the export from the individual consumers into the grid at the amount that the circuit could actually accept. So this particular system I installed about 6 years ago. I work for the utility that manages all the regional cities in Western Australia. There's about 35 of them. Each city is its own microgrid. None of them are connected to a transmission system. Prior to DERMS, we were using diesel generators for primary energy source. And as customers started putting solar on the rooftops, we would have very difficult problems with the diesel generators because they would be powered down and powered back up. So we deployed the DERMS system, and we ended up, after 6 years in one instance, that we went completely carbon off. We installed bulk storage and bulk solar, and then we used the DERMS system to manage across all the systems. That particular city now is carbon-free through the use of DERMS. This is the location that it was installed in first, 6 years ago, a town called Onslow. It's a mining port. There's a video that, it's about 2.5-minute video. I don't have time to show you today, but it's in the footnote at the end of this slide pack that if you're interested, it goes through and describes our journey of deploying DERMS in this particular location. That was our first instant. There are over 35 towns. Now DERMS is being deployed in 35 towns throughout Western Australia. So when we were implementing this, there was a lot of questions about it because it was kind of new to Australia. So customers were curious if their prices were going to go up. The government had no idea what we were doing. We thought we knew what we were doing, but what we were really doing was building a future. Now, I represent an organization that specializes in microgrid development across the Southern Hemisphere. It's called the Australian Microgrid Centre of Excellence. I've been working on this project of building microgrids for the past 15 years or so. We actually have a huge following and a huge number of members. We focus on how do we implement microgrids in a safe way using standard technology. In the Northern Hemisphere, in the United States and in Europe, there's a huge following and investor mix in microgrid development, as I mentioned, as an example, the JFK airport. I want to bring those investors to the Southern Hemisphere. So our reach is from India all the way over to the South Pacific, and we're working with various organizations that want to see how investor-owned microgrids can actually be beneficial in a number of ways. Next year, at this time frame, we're going to have our inaugural conference. So keep an eye on us, and if you have an interest in this topic, we invite you to join us. Thank you very much for your time.
Thank you, Terry, and that was very insightful. In fact, the pictographic that you shown, the video actually, before and after was very insightful. And in fact, it clearly tells how the variation in cloud cover, for example, it impacts the solar generation. That is one, the cranes coming in. And the microgrids, how, in fact, one of the points which intrigued me was utilities competing with microgrids, right? So maybe there could be a place where utilities collaborate with microgrids and vice versa, where they can provide support to the utilities. I mean, I'm talking about a transmission utility or a distribution system operator. And then there could be suitable business mechanism and ancillary support as well as in energy support as well can be provided. Yeah, sure. So this is wonderful, and going forward now, let me invite Mr. S.C. Saxena, Director Market Operations, Grid India, for his insights and views on the topic power system flexibility. Sir, please.
Good afternoon, everyone, and thank you, ISGF, for inviting me to be a part of this discussion. It's a very, very important and relevant discussion that is happening here today. Let me begin by just throwing around some numbers, As a country, we have 466 gigawatt installed capacity, and the peak demand we have met already is 250 gigawatt plus. The non-solar hour peak demand has crossed 234 gigawatts. Solar installed capacity is 102 gigawatt as on 28th of February, at the end of February, out of which nearly 17 gigawatt is grid-connected solar rooftop, and around 5 gigawatt is off-grid solar. So, just to give a feel of daily operations, we have crossed 65 gigawatt of solar generation during the daytime in the past few days only. And the maximum wind plus solar has crossed 72 gigawatt also. So you can imagine how the non-solar hours can be very, very challenging, in fact. So the non-solar hours these days are a bigger challenge as compared to meeting the demand during the solar hours. The pace at which capacity addition is happening requires us to pay more attention to the non-solar hours, where the challenge is all the more larger, in fact. Coming to the change in the availability of RE during solar and non-solar, this also calls for a lot of flexibility from all other resources. For example, thermal generation is flexing around 40 gigawatt, 35 to 40 gigawatt day in and day out, and it comes down to around 120 to 130 gigawatt on a daily basis. But for example, in the recent Holi festival day, the All India thermal had gone down to 112 gigawatt and risen to, in fact, in the evening, it goes up to as high as 172 gigawatt. So this kind of flexibility requirement is increasing as we increase the solar penetration. Apart from the minimum turn down levels, flexibility in terms of the ramp rates is also becoming all the more very important. Before I come to flexibility, I would just like to complement the point member CRC has already mentioned about minimum turn down levels being required to go down to 40%. In fact, that is the need of the hour. I would go on to say that two shifting of machines is very soon going to be the need of the hour. In fact, you look at a state like Tamil Nadu, an RE-rich state which has done two shifting of old thermal generators of 210 megawatt size of its own volition. Nobody has gone ahead and asked them to do two shifting, but the imperatives imposed by the RE penetration have led to two shifting by those generators. In fact, very soon, with the kind of low thermal generation during daytime, we would also see the requirement coming up at the national level as well. So apart from that, I was speaking about the ramping requirements. We need ramping also at this levels to change from about 1%, which are the current level, to about 2 to 3% as well. You see what happens on a daily basis, the thermal would start picking up in order to reach the evening non-solar hour peak and meet the requirement at that time. It has to start picking up right from 2 p.m. or 1:30 p.m. in the afternoon. Then only it is able to reach and peak out at around the evening non-solar hours. So the flexibility aspect is becoming extremely important. Coming to the other part that has been said here about the distributed energy resources, I go back to the number that I had proposed, around 17 gigawatt of rooftop solar, and with the big push given by the government through policy initiatives, incentives being provided for rooftop installation, this is going to become a very big challenge for the states, the distribution utilities. I would start with forecasting. This DER penetration, as it goes up, the forecasting challenge is going to go up. Both for RE as well as demand. Wherever there is rooftop installed, the demand is actually shifting out of the DISCOM network demand, and when in the non-solar hours, probably it will come back to the system. So this has two implications. First of all, how does the state plan for resource adequacy? How much to look at it? If the forecasting of the RE at the distribution level, at the rooftop level is not accurate, how does the state manage its, or balances the system at the state level? So that is one. The second part is the congestion in the new distribution network. Traditionally, distribution networks are designed for drawal of power by the consumers. Now this change in the demand drawal pattern of injecting during solar hours and drawing during non-solar hours would lead to possible congestion in certain pockets of distribution networks. So likewise, at the interstate level, I would like to give an example. We are facing this kind of scenario. Traditionally, all thermal resources were in the east and the central India, and load centers was largely in the north, west and south. The power flow was from the east to west, north to south, and those kind of things were there. But now look at RE, it has come in the opposite side, entirely in the west and the south. So we are observing, say for instance, these past few days, we are observing northern region exporting right from 10 a.m. in the morning to 1800 hours in the evening. It is exporting power to the other regions. So this transmission also has to take care of that, and it was never thought that this is going to happen. But now, of course, planning is being done in a manner so as to evacuate that area, and we are doing that at the interstate level. But this kind of problems would also be seen at the distribution level as well. Next issue is coming about the variability and intermittency. Look at an example that has happened at the interstate level. Last couple of years, we've been seeing cloud cover incidents happening. We have seen cloud cover leading to loss of 7 to 8 gigawatt of solar generation in a span of a few minutes to 1 hour or so. So if cloud cover happens, rooftop also would get affected. You've lost your resource at the interstate level, you've lost a resource at the distribution level, and the entire demand would fall on the other resources. So balancing in such cases would again become a challenge. The third aspect I would like to mention is about the visibility and monitoring of the distributed energy resources. Largely we do not have much of a visibility as per my present understanding, and with the kind of distribution energy resource management systems that we've been talking about with the previous speakers, I think it is becoming very, very important that whatever rooftop is being installed must be visible to the distribution system operator. And there should be a registry of DERs that are installed, somebody must be tracking them, and these must be bound by regulations. So that this is extremely important from a resource adequacy perspective, system balancing perspective, maintaining reserves. All those aspects are very important, because unless you have visibility, unless you have real-time monitoring, you cannot do that. Another important aspect that is happening is the storage. So storage, CA has given an advisory that it would be good if 10% of the capacity of RE is also containing some sort of storage. So chances are that the DERs, the solar rooftop, would also be soon accompanied by some sort of storage. And with that on the radar, how do we get to know the real-time data and everything on the monitoring front? Apart from monitoring, there is another aspect. From the system operator's perspective, should we have controllability of those DERs? That is another very important aspect from a perspective of control and balancing, because say if we want to obtain flexibility services, or we want to obtain demand response. So again, like I think Terry has mentioned about moving from an analog grid to a smart grid. So probably these aspects are going to require that kind of data communication, monitoring, and all those things. From a regulatory standpoint, from a market standpoint, aggregation is very important, because DERs becoming small entities, it would be good to have aggregators in place who are able to aggregate, bring this formally to a market. And for all this, the role of distribution system operators, is extremely important. Presently, we do not have distribution system operators to handle DERs. DSOs are becoming the need of the day, our need of the day basically. Earlier, as a bulk grid operator at the national level, I would have simply been very comfortable not getting into the distribution side. But now I cannot ignore it. The kind of penetration that is happening, we cannot ignore it. It is affecting our operational planning, real-time balancing, everything it is getting affected. So from a purpose of the distribution system management, registry of DERs, real-time monitoring, network congestion monitoring and management, demand response and flexibility, voltage control, and coordination with TSOs. So DSO and TSO coordination is the other domain that we need to look at. Facilitating markets. One last thing that I would like to mention about is two things, in fact. One is about the data sharing. This all DERs and the smart grids that we are talking is throwing up voluminous data. It's mind-boggling. How do you handle this? How do you do number crunching? How do you derive wisdom out of it? And what innovation can happen on that is extremely important. One practical implementation that has happened uniquely in India is that earlier we had market access for 1 megawatt and above. Green open access has been introduced where less than 1 megawatt sellers and buyers are allowed to buy and sell. And we have The smallest consumer in the Green Open Access Registry that has been registered is 0.6 megawatt, which is a group housing society. So potential candidates for DER penetration are shopping malls, airports, large group housing societies, and all these such kind of entities, airports maybe. And the smallest seller registered is 0.2 megawatts, which is a wind plant. So 45,000 plus transactions have happened, 350 entities are active, about 20 to 25 million units is being traded. How do we formalize and take it to the next level of maybe peer-to-peer trading, and a lot of other things are being talked about. So these are some of the aspects in terms of the penetration of DERs and the flexibility and the real-time operation that I wanted to flag. Thank you so much.
Thank you so much, Mrs. Saxena, and for bringing a very valuable insight in the sense, like overall from the TSO perspective, that is Transmission System Operator, which is Grid India, how a distributed resource is now becoming a cause of, I would not say concern, but they would like to monitor from the TSO perspective. Erstwhile they wouldn't, but now given the size. And it's not only about one of the DER, which is rooftop solar. Maybe when we talk about a lot of electric vehicle demand, and then they are also flexing. Number one. Number two, all the storage assets in a distributed system, distribution system, maybe at 33 kV, 11 kV, 400 volt and behind the meter, that also impacts a lot because it's all a bottom up when the load rolls up. And it also impacts the system operation and planning as well. Yeah, so and thanks a lot for the very insightful verbal presentation. Now, may I now invite Mr. Om Dubey. So he is Director CCR Australia. I think you are connected online. Can you hear us, Mr. Om?
Yes, I can.
Yeah, sure. So over to you, and if you can, yeah, thank you.
Thanks a lot. I would like to thank ISGF as well for giving this opportunity. My presentation will be very, very brief. Just giving a brief about ourselves, what we have been doing in the last few years, and how our systems and technologies can be useful for many similar topics and what we have been discussing right now. So in general, we have been in business from last 15 years. The climate change response provides ecosystem for energy systems, including intelligence and advisory services based on real-time data capture and analytics. So we have got complete end-to-end solution developed by us to capture the data, utilize for various purposes, including for DRS applications. I'm not going to detail about India's progress, which have been humongous in many terms, and India is leading in many, many ways in the energy transformation in the last many years, I should say. I worked there starting when the Ministry of Renewable Energy was opened in the first few years in '84. So it used to be called, I think, Ministry of Renewable Energy, MNRE, Ministry of New and Non-Conventional Energy Sources. So I've seen the whole journey myself and have been part in the beginning as well. So based on those experiences, doing other academic research work here in Western Australia and working in the sustainability field, we developed many things based on those experiences to see that how our systems can be utilized for various applications. Next slide, please. So the grid challenges what we talk about are mainly the variability in the renewable energy sources because they are based on the natural conditions, distributed loads, as well as the lack of the real-time coordination. The advantages what we will have with the DERMS is that we can have the real-time control, we can have seamless integration, and which can lead to the enhanced grid stability. So stability and reliability is one of the key areas which we all have been talking about. How to achieve it, that's the challenge. I must say, in case of Indian conditions, India is far, far ahead than many even developed countries, including Australia, in the digital and telecom infrastructure, which is a very key factor for the DR adaptation. So I must say that India should be leading even in the DR adaptation as such, which will is again some of the standards which you all might be aware, like IEEE 2030.5 has come into picture, and I'm sure most of the systems will move towards that as well, which will ensure the security and standardized communication and market participation, and again it will lead to the stability and reliability of the DERMS. Next slide, please. So what we have been doing, so some of the advanced features of what we have developed is in the power flexibility and DERMS include the real-time monitoring and management of grid control. So our specialization in the last 7-8 years have been in the real-time monitoring of various data, not just the energy, various other peripheral variables as well, which may lead to the utilization of renewable sources as well as the consumption of the energy data. For example, the solar radiation, environmental data, and many other variables. We also provide the advanced analytics and the multi-parametric analysis at the same time of the data which we collect in the real time. And now with the predictive AI and generative AI, those things can be much faster and useful, and reducing the processing time and by many, many times. We also provide the smart integration of various renewables, including solar, wind, battery storage, and EVs. And we also have been involved in developing the projects related with the substation monitoring for various energy efficiency purposes and automation of various other parameters to improve the whole process. So the key features and differentiations, what we have in comparison to many others is our systems are 2030.5 compliant for seamless grid integration, interoperability across various legacy systems and the modern assets as well. So we have been capable of connecting our systems to capture the data through very, very old SCADA and other legacy systems. And our systems are quite secure. We have been doing it from last 6-7 years. So remote monitoring of various type of data, forecasting them and control has been our key expertise, I should say. And our devices are not based on one particular communication. So type of energy systems. So what are the current challenges we found in the implementation of DERMS? So what we found based on our experience have been the compatibility issues and the old legacy systems. Sometime may not be in the Indian context, but many other countries, the very high workforce cost to implement them. And there are a lot of infrastructure constraints, somewhere very, very old systems. And again, when modifying to the new system, they don't talk to each other. And the grid reliability concerns due to this unsynchronized distributed energy resources have been one of the key challenges. The game changer from our side has been the development of this multi-protocol edge device, which we have been using now for almost 6 years at very, very remote sites, in very, very harsh conditions as well. But they have been, we had a lot of challenges in the beginning related with the communication, some other high temperature conditions, but now they all have been overcome and the systems have been performing extremely well in the last 4 years. So we have integrated many legacy systems, very, very modern systems into a unified intelligent ecosystem as such. As mentioned earlier, India has an advantage for early DERMS adaptation because of the robust and very efficient telecom network, which will lead them towards like many other countries. Why India should prioritize the implementation of DERMS? In my opinion, country's policies have been very supportive towards the renewable energy, starting from, I should say, 80s, when nobody was talking about renewable in many countries of the world. So India has been leading, and in many other programs, it has been leading. With full support of the government, there is a great opportunity for the implementation of DERMS at much wider level than we are now. It will increase the grid resilience, and more solar, wind and EVs can get connected to the system. It will also reduce the energy wastage, better utilization in a very optimized manner, and it will prepare the DISCOMs for the future by ensuring seamless grid integration and automation processes. Next slide, please. Just the recent project which we did just few months ago. Synergy is one of the largest government retailer here in Western Australia, in Perth. There is no competition as such because all the householders have to have no choice other than being the Synergy customer. So the project what we had was to support the storage mode pilot in line with the CSIP server what they had, and also to comply with the IEEE 2030.5 specifications. And the purpose was mainly for the BSES integration and the virtual power plant enablement. So Synergy had some of those projects in the past. They had certain challenges, and before they go into much bigger level, which they have already announced to go in the next financial year, starting from 1st of July, they wanted to do these testings and see that the system will work properly. So that's where we came into picture. We provided the solution, including our hardware and software, and we validated the Synergy evaluated the data collected through that process, and it was they had an independent testing through a solar battery, the PV battery supplier in Melbourne, and all the data and frameworks were validated for DER integration. So we have crossed that stage, and now the time is there to scale those MED deployment across Synergy's future BPP sites, which will happen in few months' time, and it will align with Synergy's 2030.5 compliant policy for new vendors. And it is being done to expand the grid flexibility, and we hope that it will enable a sustainable and scalable transition to their operations with real-time grid orchestration. Thank you all very much.
So, thank you so much, Mr. Oman, about what CCR is doing in Australia and the way you have enabled VPP rollout. I mean, that is a great learning point. In fact, must be emulated in some of the Indian cities where a lot of DERs are there, and we are also facing, like in Delhi, we are facing a lot of challenges in meeting the peak demand in terms of not the availability of power is not an issue, but the network constraint is an issue. So VPP is going to play a very important role in the overall. In fact, this brings me to another aspect which is called resource adequacy, where the demand side flexibility is not finding a meaningful mention in the overall resource adequacy framework in our country. Though it finds a mention in the overall RA planning guidelines, but it has to find some meaningful way. So yes, so DSO, demand flexibility and VPPs all are going to play a very important role, and thanks a lot for your insights. May I now invite Mr. Akilur Rahman, CTO Hitachi India, for your discourse, and may I request you to limit to 15 minutes, please.
Thank you, Abhishek, and So very good afternoon. It's always very exciting and interesting to see diverse experts from diverse countries and different utilities and experts here in this kind of forum to discuss about the power system flexibility and DERMS, and especially this topic. So, of course, this has been talked about, how the classic power systems were looking like, and I'll just refresh. So, this is working, right? Yeah. All right. So generation, grid, industry and large commercial, they were all siloed, so very predictable they were there, and earlier and even now also many parts of the grid we already have this kind of situation. But coming to future, this is going to be the very complex kind of grid, complex in terms of different type of sources of energy, different type of loads. Starting from generation, we see also more and more renewables coming, but also the microgrid distributed. Mr. Mohan already talked about how not only the microgrid standalone, but also federated microgrids. I think that is what is going to happen in future with battery energy storage. And on the right side, on the demand side, it is industry and large commercial. You're going to see a lot of electric vehicles, electrification of industrial processes, green hydrogen, and of course the mobility in terms of not only the electrification of the railways in India especially, and also in other parts of the world, but electric vehicles in different segments, whether it is passenger, commercial, mines, process industries, and of course, having the prosumers, having the microgrids at the consumption point, the prosumer, Mr. Saxena talked about the rise of Mr. Dillion also talked about prosumers. So this is going to be the future where you see also HVDC playing a major role. We have been in the country using HVDC since 1990s. Of course, for large bulk power transmission, and we as Hitachi Energy and ABB, our legacy, we have been part of this journey, HVDC journey, but in future it is not going to be just point-to-point HVDC to terminal, but also multi-terminal, and also leading to meshed kind of HVDC, networked HVDC. And why it is? Because all to make the power system more flexible. With the demand generation varying so much, not having so much of predictability, I think HVDC is going to play a major role in the grid to make it stable, make it flexible, make it also predictable. So when we are talking about renewable energy, not only on the land, but also in the sea, in the mountains. So in India, for example, we are fortunate to have renewable energy available in the terrains of Himalayas. For example, Leh Ladakh, plan to, of course, there is already plan to set up tens of gigawatts of renewable energy. But how do we evacuate them and transfer to the grid, center of the country or north of the country? And so there we are also working on studying how from Leh Ladakh to Haryana, Kaithal, how the power can be transmitted using HVDC or HVAC, and then how the design also can be met. So I think these are the challenges, but all again to make it more flexible, because on one hand you have tens of gigawatts, which is not so much predictable. Of course, we have to use the technology to make them predictable, but also ensuring that in real time we are able to control the grid and make it more sort of reliable and available. So we are talking about also the offshore wind, for example, on the western side of the country and also the southern sides. So where deep in the sea can be offshore wind, which can be again transmitted, evacuated using possibly AC or even HVDC, whereas Hitachi Energy, we have the experience in North Sea to evacuate and deliver power using HVDC subsea cables. And you also see on the demand side, the green hydrogen, the electrification, the transportation I talked about, but also HVDC being used for city in feed. For example, in Mumbai, we are working on HVDC line for feeding to the city. It's not long distance line, but 100, 200 kilometers. And that is how it is being also used, and to make it again more reliable, the power to the consumers. So there are four aspects we are seeing which is driving the power system and making it sort of more challenging in terms of flexibility, but the technologies are there to handle. Supply side, we are talking about all these renewable energy, where we have to have more predictability. Demand side, different type of loads, but active grids, for example, where we can also make the grid more sort of predictable in terms of having the grid forming technologies, grid forming converter technologies there. Energy storage, again, I think the previous speakers talked about how the energy storage is going to play a role, and also in India, for example, 10% of the renewable, the storage has to be there. So I think this is again very important. As you see here, the power electronics as well as digitalization and of course sustainable products and solutions, they are going to play a very important role in making the grid flexible. So coming to power electronics, why it is important, and we know that in the example, I think Anand talked about how in the conventional system we have more inertia in the system, in the power grid, and as we go with more and more solar energy, I think the inertia we are going to lose, the rotating mass. So then we need to bring in some kind of synthetic or virtual inertia to have the grid catering to the demands, flexible, dynamic demands, as well as generation, which may not be that predictable. So creating basically grid forming converters, so where this can actually support the grid, not grid following, which has been the conventional one. So starting from there, how we use the power electronics technology in HVDC I talked about, so integrating renewables. For example, I gave from the Leh Ladakh, from the deserts of Rajasthan, from the wet deserts of Kutch, we have been planning for HVDC lines for evacuating power, as Mr. Saxena also talked about that. So from west to east, earlier it used to be east to west. So I think that is what you see, that more HVDC lines coming up in, so for example, Khavda to Nagpur and Fatehgarh, from Badla to Fatehgarh. So these are the examples of HVDC lines coming. And city center in feed I talked about. Mumbai in feed is one example where we are already executing the HVDC line for that. And again, this power electronics playing a major role in AC/DC, grid edge. We talked about microgrid where power electronics is used, mobility, EV charging, where AC/DC, DC/DC kind of technology is used for charging the vehicles, industrial electrification, and of course the storage, whether it is battery energy storage or green hydrogen fuel cell based storage, that is also going to be very important application of the power electronics. And of course, finally in the AC system, STATCOM and enhanced STATCOM, not only for reactive power compensation, but also having the virtual inertia to create the inertia in the system, making it sort of grid forming power electronics. And then there are different technologies Of course, SVC lights, HVC, which is in a high voltage, high power level, which is important. So examples of BESS and renewable integration, Mr. Mohan already talked about the microgrids. So here are some examples. So we have, as Hitachi Energy, we have done world's largest battery energy storage system, which is 850 megawatts in Australia. Varata super battery, which is having 1680 megawatt hours. So this is again, the need was because of the South Wales, the coal-fired power plants, and then they were inefficient, hazardous, and environment, and also a lot of trippings were there. So how do you ensure that the power, the long distance transmission line, when there is a fault, there is a disruption, the power is still available with this kind of large scale utility storage. The second example is Escri in Australia again. So here again, how we have done that, the storage system with creation of virtual inertia, the virtual synchronous machine, which can support the grid with grid forming characteristic with support of power. So these are the different examples, whether it is the utility scale, long distance transmission line where there is interruption because of lightning. So how the different sources of energy, wind and solar and storage, they have been combined. And the second example is the stadium, where it is again, integration of storage, solar modules. And so offshore, again, here it is gas turbines, battery storage, how they have been integrated, and also in islands, for example, where it is again power store, the battery energy storage, the solar, and how they are working like a large microgrid, standalone, as well as connected to the grid, larger grid. So coming to HVDC, so as we know that HVDC, for example, in India, we had done northeast to Agra, almost 1800 kilometers. So that used to be the first, even now, the first multi-terminal HVDC link in the world, and we have done that. And so conventionally it is 2-terminal, here it is 3-terminal, because you need also intermediately feeding station, converter station to get the power into the line, or you can tap the power. So in future probably it will also be 4, let's say, terminals. Here you see in the example on the right side that you have between the two end terminals, you have 2 intermediate terminals where you are feeding power from the renewable, from the solar. So this is how it is going to be in future. From 3 we will go to 4, but also the meshed kind of HVDC system where they will be interconnected like AC system. And of course you also need, in addition to power electronics, you also need breakers, which we have developed, DC breakers for this kind of system. And so how do we achieve this flexibility? So power electronics, which of course is capable of having the power exchange, reverse power flow in milliseconds, but at the same time also advanced control systems we need to have, embedded control. But on the power electronics side, so again the technology is more towards how we make the power density more and more to handle more power. So that is the technology we are working on, and higher switching frequency, because the reversal of the power, you need switching frequency higher. And advanced control system again, so I talked about grid forming technology, synthetic inertia, creating that, and faster frequency response, how the system can, and of course interoperability of the different system, and also different systems from different vendors, different OEMs. So this is what is going to drive the future of grid to make it more flexible, power electronics, advanced control system. And of course, very important our colleague from AspenTech, Anand, they talked about the distributed energy resource management system, so distributed resources and how you can integrate them into a single system, integrated system, and whether it is state level, region, or in the national level, how you get this. Mr. Saxena talked about that the visibility is also required in real time from the DISCOMs to the level of DISCOMs to the transmission level. So this is again very important. And we know that in future it's not just one-time planning and you have the system for next 2-3 years, but here it is going to be more and more dynamic kind of planning, whether long-term, short-term, and real-time operations. So they have to be combined to make it more dynamic kind of planning at the same time operations. So they have to go in hand. I think technologies like digital twin will definitely help there, creating digital twin of the network, and also go on adding or sort of augmenting the system virtually even before the physically the system, the resources are there, loads are there in the system. And the whole thing again having the state or national level network manager, which is managing the entire transmission network from the storage, from the generation, transmission, distribution to demand and distributed energy sources, prosumers, and having the secure communication technology. I think we have evolved from the conventional to fiber optic based communication to now, of course, in future 5G, which can be used for at least to start with non-real-time asset performance management kind of scenarios. And so again here forecasting, we have talked about that how even AI can be used. We are using Nostradamus AI from Hitachi Energy. We have that for energy forecasting, more accurate forecasting of the energy. I think this is what the entire system, the core of AC system or DC HVDC. On top of that, the automation and digitalization, I think this is what is going to make power system more flexible. And with that, I stop here so we can have question and answer later. Yeah, thank you.
Thank you so much, Akilur Rahman, for bringing the insights on what are the technologies, the grid level, and also you talked about e-mesh, which is very interesting. So right from kilovolts to maybe low voltage level as well. Now, may I invite Mr. Devanand P, and who is Chief PSCC at Tata Power Company. Devanand.
Yeah, good afternoon, everyone. Is the presentation loaded? No, no problem. I think I had sent some presentation, but it's okay. I think most of the topics have been covered, all my predecessors. But just before I enter into the topic, I think it's very interesting, right? Whole business of flexibility and you say DRMS, we'll talk later on. The basic concept of flexibility, it brings to a single moot point, which is written in my IEGC, the first line, which says that the whole role of all our power system engineers is to provide secure and economical power to my customers, right? Now, these two factors are the basic guideline as far as any power system engineer who is sitting here, worth his salt, is working for. That at any moment of time, my consumer, whether he becomes a prosumer or consumer, that's a different part of it, but any person who is using electricity, which either a power engineer is generating, transmitting, or distributing, has to be secure, that is all time available whenever he wants it, and it has to be economical. Now these two games have totally changed, right? The moment whole dynamics have changed. Now we talked about all, I think Saxena sir touched upon generation flexibility. I think Akilur touched upon transmission flexibility. And we are all talking about DRMS to control the distribution flexibility. So the perspective which is very critical today is how do we bring in this synchronization between all. I'll just again take one very recent example. I think Saxena Sahib and Suni Sahib all would be very much worried about what has happened just few days back, that we had an incident in Gujarat where the generation failure took away a different power flow situation which caused the voltage to drop in. But the fact is that we still ended up doing some load shedding in an area like Mumbai. Can we control that by this flexibility? So the whole perspective which is to be brought in is how do we bring in that flexibility at different time frames. One, can we have this flexibility built up into my distribution system itself? That's where we have this role of DERMS, that whether we can form up a microgrid or whether we can use behind the meter storage, so that which can be brought in at this time when there is a requirement at this juncture, rather than doing something of a conventional load shedding. So I think the whole exercise at Tata Power also, what we have been doing was that, just a moment. Yeah. So at Tata Power also, what we have been doing has been that how we bringing this feature wherein we can have this integration between distribution and transmission. What we are moving away from the conventional islanding in a transmission system to protect my network, can we have some sort of microgridding, urban microgrids to be formed, so that possibly there would be a much more high scope of available generation when I want to bring the main systems to work when the system is to be restored faster. So these are few things which I just wanted to state, because I didn't want to, again, as I said, I had a small presentation, but it was more of a advertisement that what we are doing. But it made sense that at this juncture that I would say this. And secondly, on the DRMS side. Now, very honest, because DRMS, the first thing, and I really loved the fact Mr. Saxena said that today we don't have a visibility, right? Honestly, we are talking about DRMS visibility, and maybe some people may feel it bad. We do have distribution companies, DISCOMs in India, who don't have the visibility of their load. Leave aside the question of visibility of DRMS. So we need to be a bit more practical to this extent. I do understand this is a big pain. But at the same time, how do we make the information or visibility upfront? Is there a use of IoT is the right thing? Is the use of regulation is a must thing? That means if anybody is putting up a rooftop solar, possibly the necessity of that being registered and the visibility in the right form. Again, please understand, visibility in the right form is a very important factor, right? We just give a visibility, it doesn't matter, right? It should be available, and it should be available at the right place. Again, I'm just telling you from the experience of, we do run a control center or NOC for rooftop solars across India. So looking into all those perspectives, I'm just giving you this. Second part, which is very important, is again, very interesting thing which was brought in on the control part of it. I'll just share. At one more forum, there was some discussion on DRMS. I think Australia is a good area where there has been much of DRMS actually has been implemented. So one of the very interesting use case there was, which we call about the dynamic line loading, which we are talking on the transmission side, which being done for the distribution, especially for evacuation of solar on the lines. So where you are saying that, okay, any consumer who would be the participant in it would have the advantage to dynamically increase the value of generation which he can evacuate through the network. Now that's an incentive, but at the same time at the DISCOM level you are getting a control. So these type of schemas or these type of use cases has to be put in before we bring into DRMS. So as we are moving and as a progressive utility, we are also putting our foot into implementing DRMS, at least on Mumbai, Delhi areas to start with. So there we would definitely giving a complete direct investment and putting up a complete full-fledged DRMS may or may not be useful, or we never know how much of full utilization it is going to happen. So we need to find out ways and means to how to implement the same thing, but in a progressive way. I think you can say that as the time grows, we learn and improve, as we have been doing in our SCADA, DMS, ADMS, and so on and so forth. So some deployments on cloud can be looked into, but again, how do we address the cybersecurity concerns, and most of us being on the NCIPC side, so how do we actually see that the cloud usage is totally worked up? So I think these are few words which I would like to put up, and thank you very much, and I think it has been a great learning also listening to everyone. Thank you.
Thank you, Devanandan. Bringing in a very good perspective on what could be the roadmap for flexibility to be introduced, and like for example, we had a journey from SCADA, ADMS, DMS, and now DERMS. Before I call in the next speaker, give a perspective that unlike previous years where slowly the SCADA adoption happened up to 11 kV outgoing, we were having control over the grid. The need for introducing DERMS or demand side, distribution side resource management system might be more accelerated. Why? Because the rooftop solar, like for example, it's a mission modes going on. So PM Surya Ghar Yojana, and if you talk about, then the EV charging is also mission mode where masses are involved. In SCADA, the masses were not involved. There were limited interventions from main stakeholders like distribution utilities, SLDCs, and NLDC. But here, since masses are involved and therefore millions of distributed resources, therefore the pressure is there on how to roll out and create a framework. It's not like we should do or not. It's like when to do. And the better still is to create a framework and be ready, because we can't wait for all the DRs to be on board. And then we say that, okay, now we are going to decide and develop a system which how to control, monitor, and dispatch these DRs. So that will be too late. Now, may I invite Mr. Suraj Bhasin, I think he's Digital Solution Architect, Grid OS. Mr. Bhasin, over to you.
Okay, I don't look like that. That is when I moved to Dubai. But anyways, thanks. It's an honor to speak here with my esteemed panel, and the Debashish sir and Furqan Saab is here. That's how I started my career. But okay, I have a dedicated presentation on the topics that was listed within our agenda. Okay, so I don't want to say what DERMS is, but just imagine if a grid operator sitting in, let's say, an LDC or a DERMS control center has the ability to view all the DERs, whether it's rooftop, it's a CER, which is consumer energy resources, it's a DER, or it's an aggregator, which is what we call DERA. Distributed energy resources aggregator, right? I want to run power flow every 15 minutes. I want to run heuristic or ANN, and I want to see what's the limiting factor of a particular DER, and I want to control that DER. So just imagine a DRMS system within a control room doing all this ability. before I jump into some of the use cases and challenges, I moved into data science, and that's what I do, run ML ops for utilities across India and United Arab Emirates. So let's talk about challenges. I think it's the same across the region I work in, and in India is net zero. We have been told to reach net zero by a certain 2030 or 2050 target. Challenges, I have divided into three, is network capacity challenges. So EV or heating it's adding 50 to 100% to the load. There are new electrical patterns, which is backfeeding. I think Saxena Saab just mentioned that we don't really know what is the net and true load. There are hidden loads. So there needs to be a system, if there is a metering from the net metering at the consumer side, we should be able to know if that particular resource can backfeed or not. Another one, I think Mr. Theory said, was intimacy across T&D. There was a problem with the AEMO, an Australian utility, which actually had to share 210 megawatt, which is my next slide. So instead of not curtailing and using distributed or PV resources, we are actually curtailing. And it's actually just not distribution, in my opinion. It is TSOs and DSOs. We need to exchange ideas. We need to exchange that right data between DSOs and TSOs. The other challenges which I particularly foresee with utilities are the quality of service. Another example is Stedin in Netherlands. They had thousands of under and over voltage scenarios for rooftop solars, right? That is eventually affecting your quality of service. And last but not the least is we have to have DER penetration, keeping customers' KPIs the same, lower service, keeping the end customer happy. So these are particular challenges which we as a software provider are foreseeing. So is DER a challenge, or can we make DER a part of our solution for grid operators? That's what I'm going to talk a little more about. I didn't mention AEMO. So March 16, 2021, there was a cloud cover, and eventually we had to drop 300 megawatt from rooftop solar, which brought the frequency to 49.5. So it's equivalent to dropping one large generator, right? Another example is Stedin, which I mentioned, was they did have the TSO asked the DSO to curtail. Imagine that scenario, right? So that is quick examples of some of the customers. And let's say the utility now has a DERMS system. What is the control room going to do for DERMS is, the first is planning, okay? So planning can also include forecast, but I also include planning for system inertia. So there are vendors in the market which actually can have inertia metering, which is in real time, and inertia forecasting. So we need to know how stable is the grid for including DERs into my grid. So that is important. So we need to know our, obviously, generation and demand forecast, and how stable is the grid for my X number of renewables coming into the system. So that's system inertia. Okay. Okay. So now I have forecasted my load and generation. I'm going to fetch that into my DERMS system for optimization. So a lot of utilities do choose MAEs, which is mean revision errors, and identify violations. So these violations can also send dynamic operating envelopes to DERs. So what is a dynamic operating envelope? It's the limiting factor to a DER, saying that this is the limit you can operate within. So that is also a part of what our topic for today is, flexibility. Okay, so once you identify the violation, you optimize and analyze, and then dispatch to the DERs through, let's say, IEEE gateway, or OCPP, or OpenADR. So that is a quick overview of how a DERMS operator should operate, including the planning and dispatching department. Okay. I won't speak much on this, but the planning for flexible DERs is going to be add DERs into my network who are going to be flexible, who are going to have connection acceptance. So, for example, I will only add a DER. It could be a scenario in India, or it could be a scenario anywhere in the world. I would only like to add DERs which are going to be flexible, and for the DSOs. DSOs can curtail or take the whole generation as it is, right? Okay. I think this was another example of the agenda was having a global success. We as GE or Nova, what have we done? What are we seeing? What are we seeing across the utilities across the globe? So one of them was Australia, which is AEMO. They wanted to operate dynamic connection. This is what I was saying. The connection needs to be dynamic and flexible, and to maximize the customer and network asset utilization. So how did we end up with it? We also had a DER registry program, which is below on the left-hand side, and the optimization within the DERMS had dynamic operating envelopes. So that is the region Australia, Mr. Theri can add to it. That is one of the aspects. Another aspect we see is a West Coast utility. They had DER aggregators disaggregating that data from DERMS system, which is the DERMS system. So a DERMS control room doesn't need to have all the millions and thousands on millions of points directly coming into the control room. You can have an aggregator in between and let that aggregator manage and disaggregate all those particular DERs. I think I'll jump to the right one, Norway. I think Saxena Saab mentioned is we have a ton of data. we have millions of CSV files, millions of flat files. We have historical data within, let's say, NLDC or NRLDC, 5-10 years of data of weather data, generation, true load, net load. How do we clean that data? How do we make sure the data we are trying to use makes sense? I come from services too when I was 10 years ago. And whenever somebody used to ask me, okay, dump me the last 2 years of data within the control room, and we were scared. We used to run. So it is there. It's just that we need to make sure the data is usable. And that's what I do today. I do correlation matrix, I do data cleansing and data accuracy within the platform for data management. So even if you have the data, you need to know what parameters correlate to each other. And that is what machine learning is trying to do, right? You run a KNN, you run an ANN, and that's what you say that, okay, the weather as well as, let's say, the irradiance has a correlation matrix of 3 versus weather and cloud cover has a correlation matrix of 2. So tons of data available within our region. We need to make sure we use that data, edit it, VE, validate, estimate an error, cleanse it, and then boom, send it over to your upstream application for DERMS. Okay? I want to be on time. But I think this is important was, another agenda of the item was an example is Florida Power and Light. So we did a pilot with FPL, Florida Power and Light for V2G. People say V2X. So it was a pretty straightforward. It was, I think, 8 buses. 9,000 buses. They participated in dynamic operating envelopes and state of charge for winter and summer period. It was a pilot program. It used IEEE 2030.5 to communicate back to the control room. They wanted to discharge during off-peak buses hours and obviously charge on peak demand hours. So that is something being done in the United States from Florida Power and Light. To be noted, not all EV cars are subject to V2G. So for example, Tesla isn't ready, but Hyundai Ioniq is ready for V2G. Okay, last two slides, and I think everybody wants a coffee sooner or later, but if you want to build a control room of the future, we need to be proactive than reactive. We can't be reactive to, a curtailment. We need to be proactive, right? And we want to have lesser number of operators doing basic jobs rather than just doing a set control and everything else like that. So we need to have the right operators doing the right job. And we want to achieve all this with net zero and a minimal investment for hardware, right? So that is where I think for DERMS as well as the control room of the future should look like. Okay, last slide. How should a utility approach or a DISCOM approach a DERMS system? I actually divide this into two parts. One is stage 1, which is going to be planning, and stage 2, which is going to be managing scheduling / managing dispatch. Okay, so the stage 1 should include your model management, and it should also include forecasting. Model manager is where your DER registry comes into the picture. We do not want to have an Excel sheet with all the DERs mentioned and the owners and let's say the peak generation. It's over. We can't handle CSV files. So we need a DER registry, whether it's Postgres or whatever, but we need a system who has millions of DERs into one single source. Needs to be a single source of truth rather than reaching out to utilities, right? The second one, that's the first one. And we also need regulation from BIS for example, in the Australia, it's IET 2030.5, but it's CSIP certified. So India can do their own standardization. Let's say we want to have a different set points over an EV. So we need standardization coming into our country. Next is going to be gateway. That's the integration part. We need to adopt either EEE 2030.5 or OpenADR, but we need to have the right approach to integration. IEC 104, IEC 104 is all done and dusted. We need to move. We need to move to internet connections or VPCs of 2030.5 or OpenADR. The place, I was doing POC for a utility in United Arab Emirates. They were using OCPP over internet, and they were not hesitant to connect to their control room because it was secure. That's what they want to build through, right? We can't rely on 101 and 104 anymore. The next one is going to be program manager. This is where you can have your DERs to be flexible. And this is where you can tell your DERs that you are under a program from, let's say, January to March. And after that, you have to reinvent your program or you have to come back to the utility for a program. Next is going to be operation, a single pane of glass for the operators to have all their DERs into a, let's say, a GIS map, right? And last but not the least, once you have all the data, let's optimize it. And let's, on the right-hand side, which is going to be simulation. So I want to do a hosting capacity analysis. I want to know whether, let's say, a feeder going to Pragati Maidan has the right hosting capacity to allow 36 more EV charging stations. That is what is needed. We need to do hosting capacity analysis. We want to do techno-commercial reporting. We want to know whether that feeder can handle 36, 40 EVs, or we need 2 more additional feeders, or the feeder needs to be reconfigured with a higher rating, right? So that's what I had. We need to move. India needs to move fast. We need to have regulations. All the panel is here to help India get through it. And thank you, and appreciate your time. Thank you. Cheers. Bye.
Yeah, thanks a lot, Mr. Basin. And this last slide of yours love a lot in talk about the journey of DERMS for the DISCOM. And we need more such very clear slides, and maybe we need to deliberate a lot on these. Maybe the different DISCOMs would have different roadmaps, I mean some customized and all. So may I now invite Mr. Mohak Mangal, I'm the founder and CEO Pravah. Mr. Mohak, yeah.
Hello everyone, my name is Mohak. I graduated recently from Stanford, and we are a team of machine learning engineers and power system operators at Stanford who are trying to take the research that's taking place in the power systems world at Stanford and apply it to utilities and system operators. So that is the goal. My background, I'm an economist by training. Started my career working for Poverty Action Lab in rural Bihar, then worked for the World Bank and got my master's in economics and statistics from Yale. My colleague Dhruv, who couldn't be here, he's a final year PhD candidate in energy science, and his background is at the intersection of machine learning and power systems. Our advisors are Inesh, Adam, and Lincoln, who are like faculty members at Stanford. I think like enough has been said about this context, so I'll try to accelerate. What the goal of our research group is, all the research that's taking place in the power system world, often that doesn't get to the utilities and the system operators. And so what the challenge in front of us is, how do we accelerate and commercially apply that research? So like, the first thing that we did was, over the last 3 months, we've spoken with over 50 utilities and system operators, including NEOM in Saudi Arabia, Colombia, US, India, and the EU. And fundamentally, what we want to do is use machine learning to help DISCOMs and utilities develop a predictable grid. Now, this sounds simpler than it is, but that's the underlying goal that we have, because again, like all the context mentioned, I don't want to repeat that. This initially, like, so we are working with InXS on congestion analysis, XM, which is Colombia system operator, and there's just initial discussions with Tata Power and Mr. Devanand's team on load and renewable forecasting in Tata Power. The model architecture that we are building is to combine deep learning with utility data to give DISCOMs and system operators the most accurate forecasts. I'm happy that Mr. Saxena spoke about the point of forecast, because unless we have accurate forecasts, it's going to be really challenging for us to either do long-term planning or even like real-time and day-ahead planning. And how the architecture works is it ingests public as well as private data. So like weather data is public, fuel prices is public, but a lot of system operators and DISCOMs have latent variables, have this SCADA, ADMS data, and so the architecture can use that. It then runs into an optimization engine and then predicts the next state of the grid, or like state estimation of the grid, and then we roll out that forecast. You know, we were speaking about visibility. Mr. Devanand and Mr. Saxena spoke about visibility. This was a project done, a 4-year project done at Stanford, where utilities and system operators in California did not have visibility on rooftop solar. So the project was called Deep Solar, to understand how can we get visibility without asking the DISCOM about their data or without having regulations. So the idea was that they developed at Stanford a computer vision model that, using satellite imagery, understands the size and the output of solar panels across California. And this was a 4-year study where over 50 machine learning engineers and power system operators worked. It's now been open source, the data, as well as some of the weights of the models. And what now our group is trying to do is replicate the same study in other parts of the world. So we're working in Netherlands with InXS, the idea is the same. We are also like finding partners and thought partners in India to do this, so that the visibility of rooftop solar can significantly increase. And what this helps is it gives you visibility on the grid in different aspects. For example, on the demand side, you can know where would demand peak. On the generator side, we've spoken with over maybe like 20, 30 renewable generators, the IPPs, and the first thing that they said is that our forecast bands are being squeezed by the regulator, and so 4 to 5% of our revenue is just going in paying these penalties. And unless we develop these forecasts, reduce the errors of these forecasts, the underlying business models that a lot of renewable generators have, it doesn't work. And then for the distribution company, they need to know about congestion. They need to know about the different line loading scenarios. If I just briefly talk about how the engine works, there are two aspects of it, transformers and graph neural networks. Now, most of us would have used ChatGPT, and the T in ChatGPT is actually transformers. So what transformers are really good at is that they understand large, complex time series data. Now, that time series data can be load, that can be weather patterns, or that can be market signals. The output that comes is then it can help cut forecasts, which reduces any penalties or errors that the engine is making. The second aspect is GNNs, graph neural networks. Graph neural networks are great at understanding the underlying physical relationships between different nodes. And so actually what we do is, for you to understand the grid, you actually don't need to ingest a lot of data from the DISCOM in the first place, because graph neural networks can understand the relationship between a transformer, between different lines on their own, and that reduces the risk of congestion, blackouts, and improves reliability. The three use cases we are focused on is probabilistic renewable forecasting, probabilistic load forecasting, and grid congestion. These are the three use cases. We are only focused on real-time optimization because we feel this is the hair-on-fire problem for almost all system operators and distribution companies. All these three use cases then are fed into a real-time optimization engine that takes into control about frequency, market controls, and ancillary services, and that the output is better forecast, improved coordination, and most importantly, lower power purchasing costs. And so to give you an example, we worked with a Chilean system operator, and they have a lot of wind. And so their forecast errors were around 30 to 40%. And now we have cut those errors to less than 10%. And if anything, wind is much harder to forecast than solar. In India, if there is a lot of solar, that's relatively easier to forecast than wind. Yeah, we're just looking for design partners. So if this is of interest or just technically of interest, would love to speak with all of you. Thank you so much.
Thanks so much, Mohak. And just like your name, this presentation is also very manmohak. In fact, what I would say is you are speaking the right words, actually. No? So as a distribution utility operator, myself, I am wondering, if whatever you are saying is true, then many of my problems are solved. Okay? So yes, long story short, the experiments that you guys are doing using AI and ML, you are probabilistic forecasting of RE, demand, situational awareness of each of the asset, the nodes, GNN you talk about. If you are able to forecast, and then that is going to be a very important aspect in deriving the LMPs also, locational marginal pricing, and this is going to be a good thing. Of course, this is one of the bedrocks for the distributed system. Now may I invite, and thanks a lot, Mohak, right? So now may I invite Mr. Rahul Chakrabarti, Director of Professional Services, AspenTech, and then we'll have, I think we have time. We have time till 5:30? 5 o'clock. Okay. Yeah,
All right.
Anyway.
Thank you, everyone, and welcome again to the session. I think it's a great panel that ISGF has put together. It's a great combination of people from utilities, from people who are talking and working on AI and ML technologies, and also from the solution providers. So it's very, it's very nice to be part of this panel and talking about this topic. And I think as a sequence of presentation has changed, so speakers before me have covered a lot of, the topics that I was about to cover. So, and it's a great opportunity to speak here and, assimilate all of that together. So, right, so when I was getting the invitation for this topic, there were many questions that were on my mind, and one of the prime questions that stuck through till the end is, what is DERMS really? Is it another solution out there, or is it something that's becoming mission critical in the face of the new challenges that are coming up because of a lot of DR penetration and also the consumer behaviors changing in the system? Right, so I think I'll try to unpack that over the next few minutes and also try to assimilate some of the thoughts that have been shared by the speakers before. So AspenTech, whenever we are designing any product or we are talking about any solution, we are always talking about the dual challenge. So on one side, it's the challenge of providing more and more energy. And all of us in the utility sector who are at the forefront of delivering electricity and more of the energy consumption is turning to electricity as a primary energy source. So, this is becoming more and more critical, that you need to deliver more energy to the consumers and you need to do it reliably. And on the other side, we have a climate which is becoming much more fragile. I think being in Delhi or being in Bangalore or wherever you are, you can really see the impact of climate change. So whatever solution we do and whatever energy we deliver, we have to do it sustainably, but also securely and reliably, as Devanand sir was saying in the beginning. Right, so this means that we have to walk a very fine balance as utility operators and as solution providers also in this field. And this means we are moving towards a new energy landscape and is being driven by several key factors. I think one of the most visible factors here is a transition towards a sourcing of energy from more renewable sources. So we are getting more of the energy source from wind and solar and maybe geothermal in areas where it's feasible, and also other kinds of sources. And a lot of DERs are also getting added, so these are added behind the meter. But the number what Saxena sir quoted was 17 gigawatt, which is quite significant, right? I mean, if we consider that the peak demand that India met is 250 gigawatts, and the amount of solar in the distribution side behind the meter is 17 gigawatt, and a lot more is coming up under the Prime Minister's, the Yojana of around 30 gigawatts is going to get added. So even conservatively, it's going to create an impact of, let's say, 5 to 10%, somewhere in the ballpark range, right? So that's a significant impact that it can cause. And that means that we need to have a lot of visibility, a lot of control on the resources. And also we need to make sure that whatever intermittency these DRs are adding, the renewables are adding, that we have a good control on. Even on the consumer side, the consumers are becoming more tech savvy. They want to participate in the marketplace, right? They want to probably use some kind of time of use signals. So that's something that we can provide using the different technologies that are out there, and make sure that their usage is also optimized, and ultimately all of this comes together. So both the source and the demand together, it helps us optimize electric grid usage and the operations. The flows in the network, when I was at NLDC earlier, I used to work at NLDC about 5 years back. So that time we used to have, we talk about that there are a lot of HVDCs in the grid, right? So we have 13 or 14 HVDCs in our system, all India. So many of these HVDCs have been designed to transfer power in a single direction. For example, Talcher Kolar, it is designed to transfer power from the eastern part of India, where there is a lot of coal generation. From there, it transports power to the southern region in Kolar, which is close to the city of Bangalore. So because of the proliferation of renewables, what's happening is the direction of power flows are changing in the grid, right? So you would have never thought that we have to probably operate an HVDC in a reverse direction than it's planned for. Similarly, in the distribution network, I think the challenges are much more critical, because one is that the flows are getting in both directions. And also, on the other hand, you are having a lot of proliferation of DERs, which are injecting a lot of variability, a lot of intermittency. And also, I think one of the speakers brought about the topic that we are lacking the visibility. So it should not be a black box, right, behind the consumer meter. So I think these are different scenarios that are driving a lot of use cases in terms of where DERMS is becoming very relevant. And also one factor which we come across when we are talking with different utilities around the globe is that the workforce in the utility operations are changing, right? So there are people who are becoming more tech savvy. They want to use the technology to the best possible way. But at the same time, they probably are younger. They probably don't have that much of experience what others in the panel probably who are in the operations here, they would have, right? So they need a lot of agility to make decisions against systems which are continuously changing, continuously evolving. They need some guidance systems to help them make decisions proactively, what Suraj was talking about earlier, instead of being reactive to that. So how does DERMS add a lot of value here, right? So we all know that SCADA and ADMS are the technologies that help you gain visibility, help you gain control into the distribution system operations. But this pretty much stops at the consumer meter. What happens behind the meter, that's where DERMS adds a lot of value. So in a simplified way or a simple form, DERMS is a technology that helps you gain visibility, gain control, and do a lot of market also on the behind the meter, whatever is lying there. So in terms of the benefits, I think one is enhanced visibility. So getting the visibility and the real-time insights into the DER assets that are out there, getting control on them, right? So balancing the supply and demand, this is also an important aspect. Optimizing the network so that congestion doesn't happen. You know how to optimize the network using power flow studies and other aspects through advanced forecasting techniques also, so that the load that gets masked because there is some DER asset behind the meter, that's something that can get taken care of when you're using advanced forecasting techniques or when you're using some kind of artificial intelligence or machine learning techniques, what actually AspenTech also is doing a lot of work in. So these are several of the benefits that DERMS provides you. Of course, when there are a lot of DERs that are coming up on the grid and we want them, that their data to be visible, that also means that there are a lot of IT endpoints that are getting exposed. And it's all of our best interest that we know how to secure those endpoints. So, AspenTech DGM, for example, we invest in the NERC SIP standards. All of our products adhere to those standards. And similarly, there are standards like IEEE 1547/2023, which is specific for DERMS. So these are the new standards that we have to adapt all together and then work towards a more sustainable, more secure future, right? And also the last piece that I want to call out here is customer engagement. I think we are all talking about the demand side response, which can add a lot of value in terms of operations and in terms of flexibility. So that's what DERMS can also enable if the customers have an access to different signals such as time of use or other factors. They can probably shift their load usage to certain parts of the day that can make a lot of sense for them and also for the system operations. So let me talk about one use case where AspenTech DERMS has been implemented. It is in Iberdrola in Spain. So this is a generating utility in Spain who are actually using DERMS with the single goal of achieving 100% renewable integration for the Spain's grid. Right, so this is a very tall challenge and it's not an easy one to achieve here. So they started with this North Star in mind that they want to achieve a more and more renewable integration. And using DERMS, they have been able to do a lot of flexibility in the load side. They have been able to gain visibility. They have been able to gain control. And they're also using our forecasting techniques to gain visibility and manage the market interactions better. The picture that you see on the top left side of the screen, that's from a recent post from World Economic Forum. So they are talking about a concept called solar neighborhoods, which Iberdrola has recently come up with. And in this, what they are enabling is actually peer-to-peer sharing of electricity. So if you have, for example, a solar PV installed on your rooftop, but your neighbor doesn't have, you can probably share power between your neighbor and yourself. So these are novel use cases that are coming up when the right technology is in place and when there are right people who are using this technology. And I think in India, we are people who believe in frugal engineering, right? We are very ingenious people. So when we have the right technology in the hands of the system operators, I think a lot of magic can happen. In conclusion, I want to talk about the roadmap. So, DERMS, we have to consider it's an opportunity to move to a more sustainable future, right? So whenever there is any change, it's always a choice between uncertainty and on the other side, there is an opportunity. So here we have to embrace that uncertainty and ensure that we are delivering the best solutions to turn that into an opportunity. So for example, instead of having black box behind the consumer meter, we can use DERMS to aggregate a lot of DERs, club them together as a virtual power plant, and dispatch them like a traditional power plant to achieve market goals, and also help in a lot of competition to come into the market. And when competition comes, a lot of new technologies also come up, and that all helps us ultimately in the overall ecosystem. We also have a great role of regulator here. So interestingly, we have member CERC on the panel here. And I think, for example, in the US, they have a FERC Order 2222, which is allowing a lot of integrated DERs to participate in the electricity market. Right? So participate in the wholesale electricity market, that can really enable a lot of new use cases. It can enable a lot of market participants to come in and really act on this. DER registry, I think many have spoken about that this is one of the critical pieces here, and we also need to add up the advanced cybersecurity standards. This is quite critical because we are increasingly getting more IT and OT integration. We are also getting a lot of changes on the load side, right? So we are getting data centers, we are getting warehouses, we are getting malls and other things. So these are all going to get connected, and they are all contributing to the electric grid. Right, so it's very important that we add up the advanced cybersecurity standards to make sure that the entire operation is quite secure. Lastly, I would say, we are all gathered here, a motley group of people from multiple facets across the electricity industry. It's in the best interest of everyone that we all work together. We all understand that what the use cases for the utilities are, what the solution providers can provide for that. And when all of this come together, when we build awareness that DERMS is a critical solution that's needed for tomorrow, and we have to implement it today, right? Because electricity sector has a long life cycle. So everything can come together and we can achieve the best value out of it, right? So let's build capacity, let us all work together and towards a collaborative future, towards a green and more sustainable future, right? Thank you.
So thank you so much, Rahul, and for your insightful, especially the Spanish case study. You talked about peer-to-peer blockchain-enabled solar trading. I think in India also we are going to start very soon. Some of the regulators have already given the guidelines and framework. Well, with this we come to the end of the round of presentations by our esteemed panelists, and hope you had a very insightful last couple of 2.5 hours, I guess. May I now invite our session chair, Mr. Ravindra Singh Dhillon, to give his closing remarks and also summarize his thoughts on way forward.
So this has been a very interesting session, and I think from the design of DERMS to how it is to be implemented and the way forward, and regarding the flexible operation also, a lot of things have been said and has been indicated by Mr. Saxena that two-shift operation, the Commission is working on that, and I think some sort of incentive has to be given to the generators who are going to participate in that two-shift operation. So this is the work in progress in the Commission. With respect to DERMS, I think DSO, I think, has come out that we should have DSO, and we can have discussions on how to implement that and how the regulators at the state level can do it, and the FOR can, I think, some sort of standardized thing can be where, as has been talked about, the visibility of the distributed the sources is there, and then how to coordinate with the RLDCs and SLDCs. So these things, I think, is the way forward. And one of the challenges which I see with respect to having so many distributed sources is that each one of them will try to optimize their costs of consumption also and of generation also. So way forward will be that each household will have a rooftop, along with that a small battery, and then he will run an algorithm that at what time I should charge my battery, at what utilization I should do, how much power I should take. And each of them will be doing such things. Each household will be doing. On the top of it, distribution, DISCOM will be there who will try to see that how revenue gains can be there from implementation. So this is a little bit contradictory things, and I think that is the challenge which we have to look at. But very interesting session, and all the panelists, I would like to thank them that to make it very knowledgeable and interesting. Thank you very much.
Thank you so much, sir, for your very insightful way forward that we are going to do in terms of regulator and all. In the interest of time, maybe I'll just request 2 questions, if at all they are there from the audience, and then we close the session.
My name is Sunil Wadhwa. Abhishek, this is actually not a question, but something which is bothering me, right? So we're going to have, I don't know how many connections, how many resources which are just decentralized, which will be, captured in a way, monitored XYZ. So I have a very philosophical question on, is DER a means or an end? So if given a choice, you had something better, would DER be the only answer to that? Or is it something that some people feel it's imposed on us? That's first point, okay? So whether it's a means or an end, I don't know. Then there are logics for decentralized generation and distribution, both. I mean, I don't know exactly what the numbers will be, but I know, say, the remote villages of UP, for example. One of the DISCOMs, 2 DISCOMs are coming up for privatization, so some more knowledge is, coming out as to why the losses are high, the lines are very long, distance is too much. Now, I had done a calculation of electrification of villages. Electrification within the village is fine. But to get the power up to there, the transmission line payback period is close to 1,000 years. Now, and the regulator will not say no, because that's required. Otherwise, any investment you go for 1,000 years payback will be rejected. Okay. So, having said that, if the decentralized generation and distribution in some pockets of the country is resorted to, that it remains islanded in that area, where you need not take the transmission lines ever, then you won't have to really worry about the DR getting integrated, because by the very nature that you are trying to save the cost on transmission, it is not to be integrated. Okay, that's one. The third point I wanted to make, and this is quite different, is when you do the DRs, my thought was that suppose there are 100,000 points to be covered. Can it be clustered to make it only 1,000 points? So that you have 100 distributed resources getting captured in one place, and from where the DISCOM picks up. It's like, the smart meters, when you have the RF mesh, there are 500 meters connected to one head-end system, and then that becomes the collecting point for the communication. So something like that, I don't know whether you already thought of it or not, but I would have thought, a million, I mean, you count the number of farmers you have, count the number of Kusum scheme and all that. Why can't we then have 1,000, so 1:1,000 relationship, and then you really control only 1,000th of the total number of points. These are just some thoughts.
Yeah, thank you. Thank you for the question. The first one, I think you're talking about the means or the ends. Maybe somebody? Dev or anybody, whether DERs are means or end?
Very interesting question and very philosophical in nature, right? I think DR is definitely not the end, right? And DR, as the name indicates, it's basically all the technologies or systems which we have got to manage the things. So, at least the DRMS portion of it, it is basically a management system. So, and similarly, DR seems to be the means. To the end, which we feel is everybody is concerned that we are going to go away from the fossil fuels. Or in one language, if you say tomorrow, if I say an utopic tomorrow would be that everybody is generating his own generation, we are connected, all independent generators connected, where somebody is looking at, maybe the RLDCs or NLDC is looking at it and managing and orchestrating everything. Possibly that could be the end. So the DR in whatever way which we are seeing is definitely, hopefully this is a philosophical answer. Right. So just for the philosophical question, I thought that it's a philosophical answer which matters.
Thank you so much, Dev. And second one was it's more or less, maybe you are talking about microgrids, where one is grid-connected microgrid, another is completely isolated microgrid, where the return period is 1,000 years and therefore doesn't make sense for the transmission line to go there. Whenever, as and when the transmission line gets expanded, then only you can think of connecting them, otherwise they remain as a secluded microgrid. So both the things coexist. In fact, grid-connected microgrid have some economic and other technical benefits as well to the main grid as well. So wherever it is feasible, for example, urban microgrids in cities like Delhi or Mumbai. So that way. Okay, Mrs. Soni, yeah, please. One more, yeah, thank you.
Yeah. Oh, such an exalted panel, very excellent discussion. The topic is DERMS, D-E-R-M-S. R is resource. Resource means supply as well as demand. Our whole discussion, the narrative is highly tilted towards supply side. So my submission is like this. The terms like economy, security and sustainable futures, there isn't any doubt about it. But 50% of the discussion has to move to the demand. India being frugal also was said, India being agile, our demand shape must be changed to align with the solar. The regulatory order should come that no marriage functions in the night. Everything should be in the afternoon. Those kind of actions, if we take, our load shape itself will align with it. And we have proved it. In the past, some states, Andhra has inverted its load curve during the shortage period. So we have that capability. And demand response, how do we change? These are the subject matter which should be discussed much more, because tomorrow with so much of solar coming in, only supply side in my view won't do, and demand is a good resource. Why are we ignoring it? Again, I am repeating, that's only. Thank you very much.
Thank you. Yeah,
sorry, I just want to add a good news part. Yeah, good news part of it. I think MERC has come up with this regulation of demand response and demand flexibility. And that's a very good regulation because it brings in all these factors in. And very, very important factors, sir. I think possibly DISCOMs' role in demand control and demand regulation, demand response is a very, very key factor here. Well, that's also a part of the DR.
Yeah, so demand response, when we bring it down straight to technology, it becomes as if when there is a shortfall, I will ask for the response. That's again a kind of a reactive action.
Absolutely.
What I am suggesting is that our shape itself can be changed. The load curve shape should be changed. That should be the fundamental. And that is what the policymaker should be worried about. Not only the supply side and technology side. Thank you.
Thank you so much, sir. And
adding, before we go to the next question, I think the third question, if you think there is some sense in discussing that further in later sessions.
No, we can
bring down the number of
1,000 is to 1. That's what you're saying. So that the sense which I make, and somebody would like to take on it. It's kind of a microgrid microgrids connected to the main grid, and the, say, for example, a system operator is talking to the microgrids as a whole, as a unit, and not the individual components of the microgrid. Is that what your take on this is, or something else? I mean,
yeah, I mean, if you're trying to monitor and regulate, regulations, then the regulatory part of 1 million points may become difficult to manage through, I don't know what the solutions will be.
Yeah, I think Terry talked about federated microgrids,
yeah,
right?
so if you reduce that 1 million point,
microgrid.
I mean, don't reduce the points, but from the monitoring point of view, you concentrate them into, cluster them into, say, 10,000 points. Each point, connected to 1,000 points. Is that something which makes sense? Because you have this Kusum scheme and all that, the kind of the farmers have been sort of given a promise that your income will double, you will be a seller. I was a part of that scheme, by the way, but the problem was to solve some other problem. Okay.
So if I can come in here, I think you've made a valid point, and the sheer number of points increasing is the very basis on which the requirement for a distribution system operator is emerging. Because the visibility, the accountability, for instance, if you want to give an economic benefit, probably you need to go down to the each and every entity level, right? But still, from an observability, from a control perspective, from a physical monitoring perspective, aggregation is good. So here the role of aggregation again also comes in. So I think it is working, and to an extent I agree with you that yes, aggregated for some purposes, but maybe for a commercial angle, probably you need to go down to the each and every entity. That's
commercial also could be. I remember in Delhi, for example, the ABT scheme when it came in. So Delhi as a whole were paying penalty, for example. And then Abhishek's company and my company will fight, you created this problem, I created this problem. So you could have a panchayat level, say, a panchayat level means the panchayat of, in electrical terms could be your distribution transformer, whatever. That is the level at which the monies will go from the government. Now, inter se, there are 1,000 guys, who is overdrawing, who is selling, who is buying, those could be the local adjustments. I mean, this is just a thought.
Yeah, thank you so much. And now, may I hand it over back to the organizers, and over to you.
Thank you all speakers for sharing your insight, thoughts and valuable contributions on power system flexibility and DERMS. Thank AspenTech Private Limited joining us as a session partner for this session. Now I would request Mr. Ravinder Singh Dillion sir to facilitate our speakers with token of memento. Starting with our moderator, Mr. Abhishek Ranjan. Mr. Anand S. Mr. Terry Mohan. Mr. S.C. Saxena. Mr. Rahul Chakrabarti. Mr. Akilur Rahman. Mr. Suraj Basin. Mr. Devanand Pallikut. Mr. Mohak Mangal. Now I would request Ms. Reena ma'am to facilitate our chair token of moment. Thank you, ma'am. I would request all speakers to come forward for group photo. Thank you, everyone.